Hi everyone. In this video, we will see the scalar and vector control methods for an AC motor drives, which is also known as the variable frequency drives. As we know that the VFD employs two kinds of the control methods for the AC motors, which is the scalar methods and the vector methods. Then how these two methods are different, what are the advantages of vector methods over the scalar methods, and what are the simplicity being presented by the scalar methods. All these things we are going to discuss in this video. So let's begin. So VFD control methods mainly classified into two categories, one in the scalar and the vector. So therefore, first of all, the VFD, which is working on sensors and without sensors. So which methods requires the sensor feedback and which method does not require the sensor feedback. So we have the two broad classified category under this. One is the scalar control, also known as V by F control, and the other one is the vector control. So we do not have the further classification for this scalar control or the V by F control, whereas the vector control we do have the further classification. So one is the direct torque control, also abbreviated as the DTC. Other one is the field oriented control and abbreviated as FOC, and the other one is the model predictive control, which is also abbreviated as the MPC. So these three methods are categorized under the vector control methods. So what are the difference between scalar control and the vector control? As the name suggests, in this scalar control, we don't have to deal with the vector quantities, and also this method does not require any sensor feedback to work on. So it is simply controlling the voltage and frequency without knowing the position of the rotor of my induction motor or my synchronous motor. Whereas the vector control requires the rotor position precisely, and further it works on the taken feedback data from the sensor, and then all the three categories DTC, FOC and MPC, they have all these three category works differently. So let's understand the basic principle of all these techniques and what are the differences between these three techniques going forward. So let's understand first the scalar method and how does it work, which is very popular earlier, and it is still being deployed where the precise control over speed and torque is not required, or we can say the applications like fans and pumps where the precise control over the torque is does not mandatory or is not required. So there we can deploy easily VYF control. It is very simple to implement, and it is also does not involve any complexity. So first let's understand that how this principle works under the VYF control. So as we know that the synchronous speed of AC motor, whether it is an induction motor or the synchronous motor, is given by the 120 over P, where F is my frequency and P is the number of poles. So here this relation gives me direct impression that if I increase my frequency or decrease my frequency, in other words, if I vary my frequency, I can directly vary my synchronous speed, and if I can vary my synchronous speed, it directly varies my rotor speed NR. So here NR represents my rotor speed. So therefrom, just by dealing with the frequency, I can have the control over my rotor speed. However, so under this category, first let's say we have to only vary the frequency. So first method under this, that I'm only varying the frequency. So let's understand what are the implication of only varying the frequency and keeping my voltage constant. So here the voltage which we are talking about is what we are supplying or what we have given to my stator of my induction motor. Let's, for an example, induction motor. So here as the induction motor has the equivalent circuit diagram, something like the transformer, and we know that the transformer induced EMF equation is E is equals to 4.44 multiplied with the frequency, multiplied the flux, and multiplied the number of turns. So that is the induced EMF in the let's say primary and secondary. So if it becomes even, then it becomes N1, it becomes the primary induced EMF, and if this becomes E2, and then if this becomes N2, then it will become the secondary induced EMF. So here 4.44 is a constant value. Similarly, the number of turns, once I have made my motor, these number of turns are not going to change. So I can say that the induced EMF is proportional to my frequency and the flux. So therefore, the flux is proportional to my E by F. And if I just neglect the losses in the stator happening, then this E is proportional to V. So I can say that the flux is proportional to V by F. So from this expression, clearly I can say that if I am increasing or decreasing the frequency here, if I'm just changing the frequency, subsequently it will also change the flux value, and the flux value which is being set up in the air gap of my induction motor. So if the flux changes, then it will directly change my torque, because my torque is proportional to the air gap flux. So if the flux gets changes, the torque will also get proportionally changed. So therefore, taking the torque slip characteristics over here, so let's say this is the torque axis and this is my speed axis over here. So as we have already seen the characteristic of the induction motor, so taking that into account, the red line here shows my load torque. So if, let's say, for NS1, for a particular frequency, let's say F1, I have this first characteristic over here. So this is my first characteristics. So just to change the speed, let's say I'm only decreasing my frequency over here, or let's say increasing my frequency, I'm invariably dropping my flux, because if I'll increase the frequency, I'm reducing my air gap flux. So therefore, it will further reduce my torque also. So here clearly shows that the maximum torque value is being dropped. Here in the first case, the maximum torque value is this. Similarly, if I'll just further keep on increasing the frequency, it will further drop my torque produced by my motor. So here we can see that the torque slip characteristics also become very narrow and narrow as I'm going to increase my frequency. So therefore, this method is not suitable in terms of the torque, because I can change the speed, but at the same time I have also deal with the torque requirement, or the torque produced by the motor. Other part is, if I'm keep on decreasing the frequency here, I can reduce my speed over here. However, I am also increasing my flux. If I'll just drop my frequency, I am increasing my flux. So it is increasing my magnetic flux being induced by my stator windings or being set up in the air gap. So this can create the magnetic saturation of my the material which is being used to make a stator. So further, this is also not suitable in terms of the magnetic saturation. So therefore, this method is not advisable, or it is not beneficial. So to overcome this requirement, we have the other method, which is again comes under the scalar method, or it is the only method nowadays being used, which is the V by F remains constant. So the ratio, instead of only frequency, the V by F is going to remain constant. Why? Because as we have seen previously, that my flux is proportional to V by F. So if this ratio remains constant, my flux will remain constant. So this will not drop my torque created by my motor. So therefore, if I'm increasing the frequency, I have to increase my voltage in the same ratio, so that the V by F ratio remains constant. So this graph, which is being shown over here, it is, let's say this is my voltage axis and this is my frequency axis. So I have to increase the V by F in the linear fashion, so that the V by F remain constant. However, we can see that there is some kind of a voltage boosting over here. So this is known as the voltage boosting. Why it is required? Because at lower frequency, because this is the voltage boosting is only done for the lower frequency over here, the lower frequency regions, right? So at the lower frequency, if my frequency is very low, in that case, the reactance, which is X is equals to XL is equals to 2 by FL. So here the reactance value is also sharply drops down, and therefore this reactance is only was reason to create the flux. It was the reason to create the flux over here. So this reactance further, if and also this reactance drops down, and the binding resistance remains constant because it does not depend on the frequency. So the at the lower voltage, lower frequency region, the most of the maximum voltage V is being lost in the form of or across the resistance of my stator winding, because XL gets very low, and at the lower voltage the resistance of the winding is a constant, and that consumes all the voltage which is being applied at the lower frequency. So therefore motor is not able to produce enough torque which can start my motor at lower frequency and lower voltage. So therefore at lower frequency values, I need to give some minimum amount of voltage, which is known as the voltage boosting. So this voltage boosting ensures that motor produces enough torque which can rotate my rotor. And after this voltage boosting reason, I am increasing the voltage and frequency in the same ratio. So therefore V by F remain constant. And due to this, here we can see that speed is changing as I'm changing the frequency. Speed is changing, but as I'm keeping constant V by F, the torque slip characteristic is not reducing. The maximum torque that is being produced is keeping same. It is remain constant over here. All right. However, we can only increase the voltage up to the rated capacity of my motor. Why? If I'll further increase the voltage beyond the rated voltage capacity of my motor, it may burn the winding insulations. So therefore, there is a limitation that I can only increase the voltage up to the rated voltage capacity of my motor. After this rated voltage, once we have reached the rated voltage, we cannot further increase the voltage, but we can increase or decrease the frequency. So therefore, after the rated voltage, this reason where the only frequency is changing, all right, but the voltage remains constant, so therefore we can see the torque is also getting reduced further as I am increasing my frequency. I'm increasing my frequency, I'm changing the speed, that is all right, but the same time I have also have to encounter with the reduced amount of torque. So therefore this reason where I can increase the voltage up to the rated voltage, which is also known as up to the base frequency. So this up to here, this reason is variable voltage variable frequency reason, and this reason is variable frequency only, where the voltage remains constant because I cannot increase my voltage further beyond the rated capacity. So the points in terms of the suitability, V by F control is suitable for the applications where precise torque control is not required. It provides basic speed control but lacks high dynamic performance. Complexity and cost, simple and cost effective but lacks precision in torque control. Ideal for fans, pumps and conveyor where exact control is not critical. And torque at low speed requires voltage boosting at low frequency to maintain the torque, because the magnetic flux would otherwise drop due to the resistance of the winding. So now here we will discuss about the field oriented control. And in this video, we will only take up the FOC brief, and we'll take DTC separately in the another video, because FOC is the mostly widely being deployed for the control of the induction motor or for any AC motors. So field oriented control, and also abbreviated as the FOC, known as the vector control, is a more advanced control techniques that allow for independent control of torque and magnetic flux. So similar to DC motor. So because as the separately excited DC motor has two separate circuit, one is for the field and the other one for the armature. So one controls the torque, the other one controls the magnetic flux. So similar on the terms, what it does, FOC, it converts the three-phase ABC stationary frame into the two orthogonal component, which is known as the direct axis and the quadratic axis, just which kindly mimics something like my DC values. So direct axis is responsible to control the flux, whereas the quadrature axis is responsible to control the torque. So the concept of the direct axis and the quadrature axis are part of a mathematical transformation used to simplify and control the motor operation, especially in the FOC. So they are aligned with the motor rotating magnetic field and are used to decompose the motor magnetic field and current components for easier analysis and the control. The direct axis, or also known as the D axis, represents the real component of magnetic field in motor, which is aligned with the rotor magnetic field. The current along the D axis controls the magnetizing flux of the motor, or in simpler term, we can say that the current component is responsible for generating the magnetic field necessary to induce the torque in the rotor. Whereas the quadrature axis or the Q axis is oriented 90° to D axis, because they both are the orthogonal, and it represents the imaginary component of the magnetic field. Also, the current along the Q axis is responsible for producing the torque in the motor. This current component interacts with the magnetic field generated by the D axis current to create the rotating force that drives the motor. So in brief, we can say that the D axis which controls the flux, the Q axis which controls the torque. So let's understand that exactly how it is happening. So here in this figure, the solid lines which is over here represents three-phase for my rotor, and the dotted line represents the three-phase of my stator. All right, and similarly the three-phase stationary frame on ABC value, let's say these phases are the A, B and C, these is being converted into the two orthogonal component. So this is my Q axis over here, and this is my direct axis. So direct axis which controls the flux, and the Q axis which controls the torque, which is responsible for the torque control. To understand the D and the Q axis, we will have the another separate video. We will talk about all the transformations happening in FOC, how the mathematical modeling is being done. So in that video, in the separate video, we will thoroughly see that how the D and Q axis is being transformed from the ABC. However, in this video, we will briefly see that what are the transformations are required to convert from ABC to DQ axis. So yeah, we understand that in FOC something the vector values, or we can say that the stationary ABC three-phase values is being converted into the two orthogonal components, which is the DQ. But it does not happen directly or with the one transformation. However, it requires some kind of a intermediate transformations also. And once we convert the ABC into DQ axis, further we need to convert the DQ axis again into the three-phase ABC values. So let's understand that exactly how it is working. So here we have one complete block diagram. With the help of this, we will understand that how FOC works. So this is my motor model over here, and we have the encoder which gives me the rotor position, and I'm sensing the two phases. So I'm taking as of now the two feedback or the two phase feedback from A and B. Here I'm talking about ABC, like something like this, which is 120-degree apart over here. So something like this. So this is my A, B and C phases. Alright. So here I have taken the two phase feedback A and B. And what are the things I'm taking from here? I can take the voltage, I can take the current, I can take the flux linkage also. So all these values I'm taking in the three-phase quantities. So here the measured A, measured B is going through the Clark's transformation. So Clark's transformation, what it does, it converts my three-phase stationary frame into the two-phase stationary frame. So this alpha and beta has been uh, it is the output from my Clark's transformation. So this is nothing but the converting the three-phase into two-phase stationary frame. So once we have done the Clark's transformation and we have converted the three-phase into two-phase alpha beta, so this alpha beta, the two-phase, again is being converted through Park's transformation. So this is my Park transformation is happening over here. So what it does, Park transformation converts this two-phase stationary frame into the something like two component arbitrary rotating frame. So again I'm just repeating, this converts Park transformation converts the two-phase stationary frame into the two component arbitrary rotating frame, which is nothing but the D and Q. So the converted D and the Q, so here I have two loops, one output which is the D component is going into one comparator over here, the other, the Q, is being going into the another comparator. So as we have just talked or discussed that Q is component or the quadrature axis is responsible for the torque control, so this is for the torque control, and D is for the flux control. Alright, so therefore here I want that the quadrature axis which is responsible for the torque control, so I want to maximize this. So therefore I have just given as the desired torque, and I'm comparing the desired torque and the measured Q values over here, which is simply as a Q, which is simply as a DC component over here. Q and D both are the DC components. So now I can apply the PI controller over here. So this value or this error being produced through this comparator goes into my PI controller, which further gives the command, and this command, if I have to give it into the PWM over here, PWM inverter, so this further, before giving back to the inverter, it needs to be converted again into the alpha and beta frame. So inverse Park transformation is being done, and then alpha beta values goes into my PWM inverter, and which again converts the phase A and phase B and phase C value, which goes to my motor. Similarly, for the DQ, for the D axis, the same PI control is being done over here. The same command is went to my inverse Park transformation. So the Q and D being produced from the PI controller goes to my inverse Park transformation, which again converts my alpha beta command. And this alpha beta command further, if I'm just using simple PWM inverter, again has to go through the inverse Clark's transformation. So inverse Clark's transformation, which further converts this alpha beta command into again the three-phase system A, B, and C, which controls the pulses and the width of my PWM inverter. So here the PWM also we will take it separately in the next, that how does it work, how the switching is happening over there. However, in this video we have seen that how the FOC block diagram or the FOC is being implemented to control the motor. So this is something like it is the vector control is being done over here. The key differences between V by F control and the FOC control is that in terms of the control, it only controls the voltage and the frequency, whereas in the FOC, torque and the flux control is being done independently. Feedback, V by F is the open loop, whereas the FOC is the closed loop. The dynamic response is low for the V by F and it is high for the FOC. Torque control, yes, it controls the torque V by F, but indirectly, and it is very, it is less precise. And FOC controls the torque directly, and it is very precise. V by F is very simple and cost effective. However, the FOC is complex, costly, but it is having the more precise control. Applications where V by F does not require the precise control over the torque, such like fans, pumps, and the conveyor belts, whereas the FOC is being implemented in the electric vehicles, robotics, and high performance drives. In terms of the performance at the low speed, in case of the V by F, torque may drop, and that's why voltage boosting is required at the low frequency and low speed. However, in the FOC, it maintains the torque without the extra boosting. So I hope we have understand that what are the scalar and the vector control methods available for the speed control of the AC motors, and how FOC is superior to my V by F, and why it is being deployed for the most of the control mechanism where the high torque precision is required. So in the other video we will check how the transformations of Clark's and the Parks happens, and how they convert from ABC to the DQ frame, and also how the PWM inverter works on the generated switching pulses from these transformations. Thank you.